No! Who did this? Monsters. Who doesn't put caps back on whiteboard markers?
You got the cap right there.
Oh yeah, there's
On the other side.
the other side of the rag. I don't think it matters, but at least you have just a cap.
Somebody play taps. Okay. So it's been a little while since we've had a lecture. In that time, you've had an exam, you've had a project, and all of us have probably enjoyed not learning more material from class. Well, all good things have to come to an end. So, what we're going to start with today, somebody left this cap off and you're still going strong. Hang in there, little Jimmy. We're going to start off with just a recap. Now, when it comes down to it, we got a lot of stuff to cover still in this class. We're a little over a month away from the end of class, and we still have Project 2 to work on, which Project 2 is probably the project I look forward to doing most every year because it's fun. But let's just power through this. We're going to talk about, so far in this class, we've talked about power management. Okay, when we're talking about power management, we're talking about how to control voltage versus current signals. Okay, because power is voltage times current. So everything we have talked about as far as analog circuit has had something to do with power. We're calculating how much power goes into X. We're calculating how much power comes out of Y. One of the reasons why your exam had so many questions on power was because that's what everything that we've done so far is related to. If you understand power flows, you understand the systems. Now with power management, we have three real components that we work with primarily. We have resistors, we have capacitors, and we have inductors. Okay. Resistors are used to reduce the amount of current. Capacitors are used to store electric charges. Inductors are used to create magnetic fields, which can then be used to actually confer power from one voltage source to another. Everybody who has a power bank has an inductor inside of your power bank. Okay, anytime you plug something into a wall socket that charges your phone, that has to have an inductor in it. And it uses mutual inductance to transfer 120 volt AC to 5 volt or 12 volt or 3.3 volt or whatever your device takes. So all of these three, though, they handle converting power from one form to another, limiting power, whatever the case may be. Now, as we're dealing with resistors, capacitors, and inductors, we know a few things. First of all, with resistors, the component equation for a resistor is given by Ohm's law, which is V equals IR. And we know that's always true for every resistor, unless somebody tells you otherwise. In which case, then you know what the equation for the resistor is. But if it's a resistor and nobody says otherwise, this is the governing equation. Okay? The implications of this are you cannot have infinite voltage or current. Because if you do have one of those being infinite, you have an infinite amount of power consumption by the resistor. Okay? So that's just the case here. Special note on this. This does not have to be a continuous function. Okay? By itself, it does not have to be continuous. You can suddenly flip a switch and it has current flowing through it. And the jump goes from 0 to whatever the current value is. Okay? So that's just an important note to make. As we move towards talking about capacitors, the governing equation for capacitors is IC is equal to C dVC dt. Okay? One of the things that we talked about with capacitors is that you can have a sharp jump in the current, but you cannot have a sharp jump in the voltage. The voltage across the capacitor cannot jump. And the reason why you cannot have a change in the voltage suddenly across the capacitor is that because of the derivative relationship, this would create an infinite current. So what that means is that your voltage function has to be continuous. It has to be able to have a derivative at every point. You'll notice that is in stark contrast to the resistor, where if you flip a switch, it can automatically be producing a certain amount of current. Turn off the switch, it can automatically shut off. It's one of the nice things that your phones use all the time. You put a resistor in a circuit that has a digital system associated with it, you flip on a switch, you can use the resistor then to reduce the amount of power that is consumed by the circuit without adversely impacting circuit timing. If this had to be a continuous function, your phones would be much, much slower. And in fact, we wouldn't have computers that are as powerful as they do. We use the fact that resistors don't have to be continuous to produce very, very high frequency waves that come out of our cell phones, out of our computers, guide everything, and that reduce the amount of power that's being consumed by those devices. Okay? Capacitors limit changes in voltage. One of the reasons why we built an RC filter for your project 1 is that a large enough capacitor is going to limit the amount of change that happens in a circuit due to voltage. You know, if you have a voltage drop suddenly in your circuit, that capacitor is storing that voltage. It's going to continue to supply voltage to the circuit by discharging. So this is a handy function. You can build filters out of it, that sort of thing. Last component is inductors. Okay, inductors live by the guiding function VL equals L DIL dt. Here, the voltage across the capacitor cannot suddenly change, but the current through the inductor cannot suddenly change. because by doing so, it would create an infinite voltage. Okay, so following here, in the capacitor, voltage must be continuous, and in an inductor, the current must be continuous. Okay. All right, any questions on this? This should all be review. Okay, we're going to do a little bit more review, and then I'm going to sucker punch your brains. KVL and KCL. When are they true in a circuit? Always. Why always? It's physics principles. Physics always has to be true. So it doesn't matter what circuit you're using, KVL and KCL are always true. Doesn't matter if it's a first order circuit, doesn't matter if it's a second order circuit, doesn't matter if you're using an LED, doesn't matter if you've plugged in a nuclear power source. Okay, KVL and KCL always have to be true. Okay, that's an important note to make. Lastly, the last note that I want to make is when solving higher order systems, what do you solve for? Which of these values? In an RC system, what did we always solve for? It was always voltage across the capacitor. Okay? What about in an RL system? IL. Okay? The reasons why we do that is because these functions have to be continuous. If you solve for the continuous function, you can figure out everything else from that. The equations to derive both of these equations are the cleanest. You can solve everything from that. So in a system, if you aren't solving for VC or IL, you're going to be struggling mathematically. And you'll find out very quickly something went wrong. Okay? Okay. Now, this is all of the review that I have for you right now. So we're going to take a break. And I'll see you back here in 10 minutes and bring your brains because